In our third lecture, we're going to introduce something called the covering space. If you've never studied algebraic topology before, then this will probably be something new. The previous lecture, we talked about the fundamental group, and that possibly might be familiar to people in other topology courses or topology books. But covering spaces, that's something that generally comes up in an algebraic topology course. Now, before we define what a covering space is, it would be helpful to talk about path connectedness again, because we're going to be using its properties when we get to covering spaces. So let's mention some stuff we need to know first. Let's begin with this definition. We mentioned this definition last time. We say that a space X is path connected if and only if for any 2 points, P and Q in X, we can find a path. And you have to recall what a path is. So a path is a function from the unit interval into X. So this is a path in X. And for some reason, and I do not know why that is, but oftentimes when people talk about paths, instead of calling them by the letter F, they often call them by the letter gamma. Maybe you've seen that before. I do not know what the origin of this is. So there's a path gamma. So this is a continuous function from the interval into X with gamma at 0 is P and gamma at 1 is equal to Q. And of course, sometimes when you look this definition in other books, instead of having the unit interval, they might have an arbitrary interval. But of course, if this is from, let's say, from 5 to 10, you can always rescale it, reshift it back so it goes from 0 to 1. So that is what we call a path-connected space. And we didn't say that there is a difference between something being path-connected and something being connected. But we're going to try to avoid talking about what it means to be connected as far as possible. Hopefully, we do not even have to bring it up, because otherwise we have to do more point set topology, which we would rather not do. The next thing that I would like to mention is something called the path component. So this is the definition from last time. So let me remove this because this is old familiar. Now let's make a new definition. We're going to talk about a path component. Now before we write down this definition, let's look at this example. Let's say that X is a union of these two regions. Okay, that's what X is. So in this example, X is some subset of R2, and it's a union of these two regions. And notice you have these two pieces, and this is disconnected, because if you have a point P and you have a point Q over here, intuitively it seems clear that there is no path from P to Q that stays entirely in X. In fact, you had a problem like that on your homework. So this is something that is not path connected. Okay, so by in this example, we can see that X is not path connected. However, these two pieces over here, this one and this one, these are called the path components, because they happen to be subsets of X and they happen to be path connected. So X is not path connected, but in this example, it has two path components. It has two subsets that are path connected, and these two subsets completely cover X. So every point in X falls into one of these path components. Now, before we write down this definition, let's just look at this picture. So let's say we were to draw the following region. Maybe I should use a different color, which is easier to see. Let's say we were to draw this region. So if you look at this picture, this subset of X is path connected. But it is not a path component. Like, we want to be able to say that X breaks apart into two subsets, both of which are path connected. Now, we do not want to use something like this as part of our definition of a path component, because there's something larger which it is contained within. So this is going to be the motivation for the definition that we're about to write down. This is the way we make the idea rigorous. We do not want the red region to be a path component, because intuitively you would not call that a component, because you can go further out. You can go all the way up to that region, and that is the one you want to call a path component. So here's the definition. Let X be a space. So we say C, so C is a subset of X, is a path component, so C for component. And just to be careful, we're hopefully do not have to use this, but in point set topology, one sometimes talks about connected components as opposed to path components. And they're defined similarly, but then you have to do other things which we'd rather not do if we can avoid them. So we say that a subset is a path component if and only if C is path connected. So it should be path connected, and C is maximal. So if you're unsure what this means, in mathematics, there is a difference between a maximum and a maximal. So this is what the difference between maximum versus maximal. Maximum means larger than everything. And maximal means there is nothing larger. Now, at first, you would think that these mean the same thing, but let's just look at this particular example. Let's say that X is a discrete space, and it contains just two elements, 1 and 2. And, well, maybe that's not the best example. So maybe I can just draw pictures of like sets. Let's say you have a set like this. Well, let me do it like this. Let's say you have this set, and then you have that set sitting, and then you have this set sitting inside and that one sitting inside. Then you can see that the set on the outside is larger than these three. But what if you have the following situation? What if you have a set like this, a set like this, a set like this, and then you have a separate piece right over here? Then in this picture, you can see that this portion, this set, it does not contain that one. So you would not call this a maximum for sets because it's not containing that one. But you will call it maximal. There's nothing larger than it. Like this one over here is not maximal because it's sitting inside something bigger. And this one will be maximal because there's nothing bigger that contains it. So the way you make this precise. Now, by the way, if a set is maximum, then it's maximal. But if something is maximal, does not mean it is a maximum. So it only goes one way. C is maximum, so that would just maximal. So that would mean i.e. if C prime is another path connected subset of X, and it contains C prime, then C prime has to be C. In other words, there's nothing larger than C. So C is a maximal path component. So that's basically what it is. A path component is a maximal path connected subset. It's path connected, and secondly, there's nothing larger that is path connected and contains C itself. So if something contains C, then the only way it can contain C if it's C already. In other words, the trivial containment. So that's the definition of a path component. And I want to get to the following fairly simple proposition regarding path components. So here's a proposition. Let X be a space, topological space, or a metric space, or a subset of Euclidean space, whichever one you like. And let Ci So there's going to be some collection. Let Ci be the collection of all path components of X. Let Ci be the collection of all path components. So what are path components? So these are subsets of X. So let's just indicate this, i.e. Ci are subsets of X. Let's write it like this. They're subsets of X, and Ci are path connected. Path connected. And let me just say maybe maximally, maximally path connected. So maximally path connected subsets. So that's what it means to be the path components. So you find all of the path components. In the picture that we drew earlier, we only had 2 path components. You could have 1 path component. Namely, if X is already path connected, then its own the subset of X, namely itself, will be a path component, because that's as big as you can go. X is your universe. So if X is path connected already, you have 1 path component. You can have 2, you can have 3, you can have an infinite number. We'll actually see an example how you can have an infinite number of path components. So that's why I'm not calling it like from like, let's say from 1 to n or something like that, because it could be an infinite number. So you have some infinite collection of path components. Possibly, I should say, possibly an infinite collection of path components. So then the following properties are satisfied. So the first one is overloading notation. This is an I, and that's just number 1. So this family is pairwise disjoint. So in other words, if you take 2 indices in your indexing set, I, and the 2 indices are different, then Ci intersect Cj will be empty. They do not overlap. And if you think back to that picture that we drew with 2 regions that were path connected, you can see from the picture they're not overlapping. So that kind of makes sense. The second thing is X decomposes as a union of all of these path components. So X is a union of all of those path components. So this, by the way, is a disjoint union based on part 1. Disjoint union just means that it's a union of sets that are non-overlapping. That's part 1. And then part 3 would say that each well, I guess I'm just going to leave it at part 1 and part 2, and then I'll get back to part 3. So let's just prove part 1 and part 2. So let's look at part 1. Okay, part 1. So proof of 1. Proof of 1. So let Ci and Cj be 2 different path components. So we're picking 2 different ones. Okay, I and j, 2 different indices. We want to show that Ci intersect Cj is empty. So suppose otherwise, so we're going to do a proof by contradiction. Suppose otherwise they had a point in common. So there was something common to both of them. So here's a picture for what we're about to do. So this is Ci. This over here is Cj. And there's a point P in common. And so let's say Y be the union of both of them. Now looking from the picture, before we write the proof, looking at the picture, if you were to take the union of both of them, Ci and Cj happen to be path connected because they are path components, so by definition they are path connected. It makes sense that if you take the union, because they have an overlap, Y would also be path connected. So the idea is that Y is path connected. That's precisely because they overlap. If they have a point in common, they overlap. And then the union will be path connected. But then Y strictly contains Ci and Cj. Because you see, Ci is not equal to Cj. So when you take the union, you're not taking the union of the same set with itself. It's a union of two different sets. So when you take the union, you're getting a set which properly contains Ci and Cj. Okay, and what's the problem? But this contradicts that Ci and Cj were maximal, because path components were path-connected subsets that were maximal. And you just constructed something that is a path-connected subset of X, and it is strictly larger than both Ci and Cj. So it just remains to show why Y is path-connected. So we just need to justify that Y is path connected. So we pick 2 points, let's call them X and Y in Y, and we will show that there is a path gamma. So a path is a mapping from I. Okay, the notation is funny because we were using previously I for the indexing set. So maybe to use slightly better notation, into X. I'm sorry, not into X. It's a path in Y. So that gamma of 0 is X and gamma of Y, I'm sorry, gamma of 1 is Y. So you're going to pick 2 points in Y. Now, because Y is a union of these two, when you're picking X and Y, the X and Y is coming either from that one or that one. So there's cases to consider. So let's just consider the case. Let us just consider the case when X is from Ci and Y is from Cj. There's really 4 cases you need to consider, but they're all very similar. I think this is the most interesting one, where they're coming from 2 different path components. And then from the picture, maybe you already see an idea of what to do here. If X is over here and Y is over there, the way you construct the map, the path, is you first construct a path from X to P, and then you construct a map from P to Y, and then when you juxtapose them together, you get a direct path from X to Y. That's the basic idea. So since X is in Ci and P is in Ci, this is where we're assuming that those 2 components, Ci and Cj, have something that have a common point, P in common, and Ci is path connected. There is a path, let's call it gamma 1. Maybe let's call it gamma I. Well, maybe just call it gamma 1. There's a gamma 1, and it's a map from 0, 1 into Ci, so that gamma 1 of 0 is X, and gamma 1 of 1 is P. And then likewise, there is a path gamma 2 from 0, 1 into Cj, so that gamma 2 of 0 is P, and gamma 2 of 1 is Y. So then, now here's the whole point. Ci and Cj are both themselves contained in Y, because Y is their union. So that means you are permitted to enlarge the codomain. So this is also correct to say. Gamma 1 is a path in Y, and gamma 2 is a path in Y. So then if you juxtapose the paths together, this is juxtaposition, this is when you put the two paths together, you would have created a path from 0, 1 into Y, which is a path from X to Y. And that is what we wanted to show. So let's just go back to what we wanted to show. We had to pick 2 points and construct a path connecting them, and that's exactly what we did. So this justifies proof of part 1. Proof of part 1. So now let's prove part 2. And fortunately, part 2 is very, very easy to prove. Let's remove all of this. So part 1 was slightly harder. This one is easier. We want to show that X is a union of all of its components. So proof of 2. So clearly, X contains the union of all of its components, since X contains every component, because the components by definition are subsets of X. So now we have to prove the reverse direction. So now pick a point in X, and you observe that the point belongs to the singleton set, the set that contains that point. Furthermore, the singleton set is path connected for obvious reasons, because if you pick 2 points in the singleton set, they're the exact same point, and you have a path from the point to itself by using the constant path. So singleton points are always path connected. Not very interesting. Is path connected. And now let Ci be a maximal path connected subset of X, which contains this singleton set. You see, this has to do with maximality. The single point set, it could be maximal. It could be that the singleton set, it is path connected, and maybe that is a maximally large path connected subset. It's not part of anything larger, but it could be part of something larger. So maybe there's something that's larger than it, and then whatever that object is, maybe there's something larger than that object. So you just pick you look at all of the ones, right? You basically consider all, if you're bothered by this, like how would you show that? Here's the way you can do it. So maybe more carefully, you construct the following set. You construct the set C, so these are going to be subsets of X with the property that C contains the singleton point and C is path connected. Okay, so you consider the collection of all C that contain the singleton point. This is a non-empty collection because P is already path connected. It could happen that this set is maximal, and then this collection of C would just be the singleton set. And then what you do next is you then take the union and then you take the union over all of these. And then you would take, and if you take the union over all the C, where C contains P and C is path connected, then this union is maximal. That would be a path, because you're taking the union, you cannot go any bigger. So you've just constructed something that is a maximally large path connected subset. The reason why you know it's path connected is because each of these is path connected and they have a point in common. And that's what we proved earlier, right? That was the proof from earlier that if you have sets that are path connected and they overlap, then their union would be path connected. So that's basically what we've shown. Okay, so that's part one, part two. There's also a third part, but it's not always true. There's a third part. There's an additional hypothesis that you need for part three. So this is going to be part three. So I'm going to write down what the third part of the proposition is, but then we'll talk about the hypothesis that we need. So the third part would say that each path component Ci is an open subset of X. Now this one is not always true. It's sometimes true, it usually is true for the kind of spaces that we deal with, assuming the space is not too bizarre, but it's not going to be always true. I would like to show you an example of when it is not true, and then we will give the necessary hypothesis for it to work out. So here's an example. Q, so Q is a subset of the real line. What are the path components of Q? So let's draw a picture. Maybe this will help. So this is the real line. And when you visualize the rational numbers, well, they're just a bunch of points that are like everywhere on the real line, but they never kind of come together. So intuitively, the path components will be single points. But you can maybe see what's going on. If you pick some rational number Q, then no matter how small you make that little neighborhood, no matter how small you make it, it will contain an infinite collection of rational and irrational numbers in there. So that's the reason why it's not path connected, right? No matter, so let's just say this, no matter how small you draw an open interval around Q, it will always contain rational and irrational numbers. Well, that's actually that's not what I want to say. That's true, but that's so ignore this. Ignore this. So we claim that the only path components of Q are singleton subsets. How do you prove this? So say C was a subset of Q, was a path connected subset of Q, and it had at least 2 points. Let's call those points Q1 and Q2, 2 rational numbers in Q. Okay, so since C is path connected, there is a path gamma from 0, 1 into C with gamma of 0 is Q1 and gamma of 1 is Q2. And now we're saying C, right? But C is contained in Q, so you could replace the codomain by just Q. And what's the problem? Well, the problem is this contradicts the intermediate value theorem from calculus, because Q1 and Q2 are two different rational numbers. So basically you pick any irrational intermediate value between Q1 and Q2. So between any two rational numbers, you can find an infinite number of irrational numbers. So pick any one of those irrational numbers. So by the intermediate value theorem, this is a continuous function. And if you pick something between Q1 and Q2, there has to exist some moment in time between 0 and 1 that will take on that intermediate value. But the problem is, gamma is a path in which it only gives you rational numbers. It never realizes any irrational value. And that contradicts the intermediate. So that's not possible. So a path connected subset cannot contain 2 points. Okay, so if you have a connected subset, it has to contain, it can only have one element in it. Unless, of course, this is the empty set, but that's too silly to consider. So the path components are singleton sets. So let me say that again, because if you have a connected subset of Q and it has at least 2 numbers in it, at least 2 points in it, then it's no longer path connected. So the only connected subsets of Q, other than the empty set that's too trivial to consider, are the singleton subsets. But the singleton subsets are automatically path connected. So therefore, those are the connected components, right? So you would say that Q is then equal to a disjoint union of all of its connected components. Its connected components are singleton sets, and it's a union of all of its singleton sets. So both conditions of the previous propositions are satisfied, that a space, a topological space, is a union of its connected components, and secondly, the connected components are non-overlapping, which you can see here. But the third claim, that the connected components are open subsets of Q, that's not true in this example. And you can see what the problem is, because what does it mean to be an open subset? So maybe we should just recall this. So an open, so let's say, like maybe say this more generally, if X is contained in another topological space Y, U is an open subset of X if and only if U can be written as V intersect X, where V is open in Y, right? This is what you call the subspace topology. So if you have a topological space Y and X is a subset, that subset inherits what is called the subspace topology. And the way the topology works is an open subset of X, it can always be written in the following form. It's an open subset of X, it's an open subset of the ambient topology intersected with X. So how do you find the open subsets of Q? You're going to take the open subsets of R, but the open subsets of R are those sets that contain the open intervals. So if you choose if this is your point Q, and you pick an open interval that contains Q, no matter how small you make that open interval, if you intersect it with Q, it will contain an infinite number of points. So no matter how small you try to make that open interval, you can never narrow it down to just Q itself, because there's an infinite number of rational points over here. So you can keep on sliding the blue closer and closer, but every open interval that contains Q will contain lots of other rational numbers there. So the singleton set Q is not open, right? Because Q, you're basically saying this: if Q is open in the set of rationals, then Q can be written as something that's open in the real line intersected with Q. So whatever this open set is, it has to contain Q, and an open set contains an open interval. So if you draw that open interval, you can see that if you take this open interval and you intersect it with Q, there will be an infinite number of points here, and you can never narrow it down to just a single point. So those are the path components of Q. And you can see that the path components are not actually open. They sometimes could be open. So this brings us to a definition which will seem a little bit strange at first. Let X be a space. So I'm going to write down the incorrect definition first, and then I'll fix this. I want to write down the incorrect definition first because this is what you would think based on the way it sounds, but then we're going to modify it. We say that X is locally path connected if and only if for any point P in X there is an open set U, an open subset of X, with P in U and U path connected. So path connected subset. That's what you would think, because you are saying locally path connected. It's path connected on a local level. What does it mean to be on the local level? That means on the level of open sets, that you can choose a small enough open set where things work out. And you can do that locally at every point. So you pick a point, you can choose a small enough open set that contains that point, and that open set is path connected itself. Unfortunately, that's not the actual definition. It's kind of funny. So this is the correct definition. We say that X is locally path connected if and only if for any point in X and any open set containing the point and any open set U with P containing the point. It's not necessarily true that the open set is path connected itself. But what is true is we can find a smaller open set, V contained in U. By the way, there's no ambiguity. Is V an open set? Is V an open subset of X, or is V an open subset of is V an open subset of U, or is V an open subset of X? What do we mean when we say open set? There's no ambiguity. An open set of an open set is an open set. Like it's transitive. So I'm sure you know that what I'm referring to. That's not an issue here. But anyway, we can find a smaller open set V. So smaller means it's sitting inside U. It contains the point, and V is path connected. So that's the actual definition. So basically, every open set around P can be shrunk into an open set which is path connected. So let me give you, now here's the part which is quite bizarre, really, really bizarre. You would think that if something is path connected, it is automatically locally path connected, because when you're saying something is path connected, you're saying something is path connected on like a global level, that for any 2 points you can find a path. But surprisingly, and this is kind of funny, you can have a path connected space which is not locally path connected. So this is sort of bizarre, but let me just show you. So you can have a path connected space which is not locally path connected. As bizarre as that might seem, and let me give you an example. Now, I'm not going to use the previous example with Q because Q is not path connected. It's also not locally path connected, but I think this is a more interesting example to look at. So here's your space. You can call this the infinite comb. So it's like a comb. So you draw something at 1, then you draw something at a half, then you draw something at a quarter, then you draw something at an eighth, then you draw something at a 16th, and then you draw something at 1/32nd, and you keep on doing this. It sort of goes like that forever. And yeah, you just keep on attaching an infinite number of combs like that. And the space is path connected, because if you pick a point, let's say on this piece of the comb, and you pick a point on that piece of the comb, you can get to them very easily. You just go down like this, right? You just go down, you go across, and then you go back up again. Right? So you can always connect them by a path. That's not a problem. The problem would be that it's not locally path connected, because let's say you pick so you do this forever, right? You do this forever. Okay, so sure. So you do this forever, and you also include the limiting. So basically, you can see these go down to 0, right? They're going down to 0. So you're also going to include what happens in the limit. So you're going to include that one as well. That's the one that happens in the limit. This is like 1 over infinity in a way. But the point is, you have an infinite number of these lines that sort of are approaching it like that, right? There's an infinite number of lines approaching it. And for the reasons that we've just said, this space is path connected, because even if you pick a point on this infinite line, that's on this limiting value, that's not a problem. You can just go down and then go across. That's not a problem whatsoever. The problem occurs when you try to check the locally path connected condition. So here's the locally path connected condition. Let's pick a point on this red one. And to be locally path connected would mean that if you pick an open, so let's suppose I draw a little open disk around it. Now notice that if I draw that open disk around it and I intersected with my space, okay, so x does not include the plane, it just only includes these lines. If you intersect it, you get this disconnected, you see, because the only way these lines are connected are down here. So if this disk is small enough, then you're picking up all of these disconnected lines. And it does not matter how small you try to make it, it will always be disconnected. It will always be disconnected. So you can never take that open disk and shrink it small enough that when you intersect it with x, that you end up something that is path connected. That you can do this with the other ones, by the way. So the whole issue occurs on the red one. If you do it on, let's say, 1 over 8th, then yeah, you can do it. If you do it on this one, which is 1 over 8, if you draw this small enough, then it's not intersecting anything else. It's only going to intersect that line, and you're getting a line segment, and the line segment is going to be path connected. But the one in the red, because the other ones get infinitely close to it, no matter how small you try to draw that disk, you get that infinite stack of lines. So you have that it's not going to be path connected no matter how small you make it. So it's a bizarre example, but that is what we call locally path connected. And I want to add something to the proposition. So let's go back to our proposition that we had from before. Let X be a locally path connected space. And for the purposes of this class, one can say that all of our spaces are going to be locally path connected, because usually in algebraic topology and in topology in general, the kind of spaces that we care about for the most part are manifolds. And manifolds, as we will see if you do not know what that is, they are going to be locally path connected. That is not a problem whatsoever. So let X be a locally path connected space. Okay, so now we can say that. So if C is a path component of X, then C is an open subset of X. So in other words, the path components are also open subsets. And I'm going to leave this as a homework problem. I think this is a good homework problem. I'll give you the basic idea of how this works. So let's say C is your path component. The common way you typically prove that something is open is you pick a point in C. So if you go back to metric spaces, how do you show that something is open in a metric space? You pick a point in a set, and you argue that you can draw an open ball or an open disk that is centered at the point, and that entire ball or that entire disk, depending how you wish to visualize it, sits inside your set. So this is sort of the same idea, but a little bit more general. You pick a point in C, and you try to argue that there's an open set that entirely sits, that contains the point P, and it entirely sits inside C. And if you can do that arbitrarily, regardless of what point you pick in C, then that would mean that C is an open set. So that's the common way you show that something is open in a topological space. But this is where you're going to use the fact that X is locally path connected. So P, there's an open set that contains P, namely X itself. X contains P. That's like the extreme example. X contains P. Because X is locally path connected, that would mean that there's a subset, an open subset of X that contains P and is path connected. So that's the definition of locally path connected. So there's an open subset. Now, if the open subset falls within C itself, then you win. But what if the open subset, let's call it U, that's U as a path connected subset, falls outside of C also? Well, then you run into the problem that we saw before, that if you take the union between C and U, because U and C are both path connected and they overlap at P, you've just constructed something that is larger than C itself. And then you're contradicting the fact that C was a maximally large path component. So that's the reason why all open, well, not just open sets, but all path connected subsets must stay within C. They cannot go outside. And since X is locally path connected, there is an open set that will contain P, a path connected open set that contains P. And in order to avoid contradicting maximality, it has to stay within C. And then from there you can argue that therefore C is open. So that's like the basic idea of that. I leave the details up for you to try to figure out. So now that we have said quite a lot of things about path connectedness and path components and local path connectedness, now we're going to move on to the next topic. We want to get to covering spaces, but before we get to covering spaces, it would be helpful to first mention something called a local homeomorphism. Before we give the definition of what a local homeomorphism is, let's remind ourselves what a homeomorphism is. So recall that a function, a continuous function, of course, between two topological spaces is a homeomorphism if and only if F is a bijection, if U is something that's an open subset of Y, then F inverse of U is an open subset of X. That's just continuity. That's the definition of continuity in a topological sense, that if you take something open here and you pull it back, you get something open over here. But the other requirement is that F is an open map, that it sends an open set to an open set in the forward direction. And this is saying that if V is something that's open in X, then pushing it forward is something that's open in Y. So basically, F establishes a one-to-one correspondence between the points of X and Y and the open sets in X and Y. Because a topological space does not just consist of points, it also consists of open sets. So the function establishes a one-to-one correspondence between both of them. So it's a bijection between these two and a bijection between these two. If something is open in y, you can pull it back to be open in x. And if something is open in x, you can push it forward to be open in y. So it kind of goes back and forth. And so it's essentially the exact same space. It's just written in a different language. So that's a homeomorphism. Now let's define what a local homeomorphism is. Definition: let F be a map between two continuous map, of course. We will be lazy and not write the word continuous. If it's not continuous, we will make it extremely explicit that it's not continuous, but otherwise you should assume continuous. So let F be a continuous map between two topological spaces. We say that F is a local homeomorphism if and only if for any point that we pick in X, we can find an open set. So let me draw a picture. Let's say this is X, let's say this is Y, and this is our map, continuous map F. So local homeomorphism means it's locally going to be a homeomorphism around every point. So if this is your point P, this is the image of that point F of P. And what we're saying is for any P in X, we can find an open set U in an open set in X and another open set in Y. So you can find an open set over here and an open set over there. Both of them contain these 2 points where P is in U, F of P is in V, so that F will map U to V homeomorphically. So when you restrict the function to the smaller set, it will map U to V homeomorphically. Now, some people might be bothered by this notation because we're using the letter F again. Technically, this is a different function. It has a different domain. So maybe to be a little bit more appropriate, we should write restricted to U. This just means F restricted to U. This is the same exact mapping, but it's just on a smaller subset. So you now have a mapping between U and V, and this is a homeomorphic mapping between those two. So that's what we call a local homeomorphism. And let me give you an example. I think it would be probably better to give you an example of something that is not a local homeomorphism. That's probably going to be more helpful, because the other examples, when we get to covering spaces, they're going to be local homeomorphisms. But we want to give maybe more helpful to give something that is not a local homeomorphism. So here's an example. Maybe we should say a non-example. So consider the following map from R to R. And this is the map that squares X squared. F is not a local homeomorphism. So let's draw a picture for what's the problem. Maybe you can already see what the problem is. So the horizontal axis represents R. The vertical axis also represents R. And we visualize this like that. Now, let's say you pick this. This is P, and then this is going to be F of P. Now, I think we can agree that if you pick a small enough, you can draw 2 small enough open intervals so that this one is mapped homeomorphically to that one. This one is being mapped homeomorphically to that one. This is like a one-to-one function. It's continuous and all that stuff. But the problem occurs at the origin, of course. So if P is at the origin, then F of P is also at the origin. So it's the same point, it's the same number. But notice that no matter how small you try to draw something in the domain, in the codomain, when you look at its image, it's never, I mean, basically the picture is this interval on the horizontal axis the squaring function, it sort of glues both of these sides together. You get 0, and it goes like upright like this. And the point is that the positive piece and the negative piece, they get glued together, so the function is not a bijection. So it's not even locally a bijection at 0. So this is an example of something that's not a local homeomorphism. The other points in R do not pose a problem. The problem occurs at the origin. That's where things go wrong. Actually, that is also the place where the derivative vanishes. In fact, maybe for people who are interested, there's something in calculus called the inverse function theorem, and I figure maybe I should just mention it for the sake of completeness. I do not think we're going to use it at all in this class, but maybe there's something nice to note. This is the inverse function theorem. Maybe you've seen it, but it's just something that's nice to know. So say f is a function from Rn to Rn, so from the same dimension to itself, is a differentiable. Let's just say it's a smooth mapping. So smooth means it's infinitely differentiable. You can take as many derivatives as you want, partial derivatives. So this function has n components, and you can differentiate it to n different variables, and you can do it as many times as you want. Smooth mapping. This is the reason why it's not exactly appropriate for this class, because in topology we talk about continuous maps. Though later in the class we will talk about manifolds, and when we talk about manifolds, you could talk about smooth mappings at that point. However, I do not think we're going to be using the inverse function theorem anyway, but I just want to mention it. So say you have a smooth mapping, and let P be a point in Rn, so this is like a vector with n components. So if the derivative at P, now you're not going to say the derivative is non-zero, that does not make sense. The derivative is going to be an n by n matrix. This is an n by n matrix. It's called the Jacobian matrix. This is when you take, so the function has n component functions, and there's n variables to differentiate with respect to. So if you differentiate each of the component functions with each of the variables, you get what is known as the Jacobian matrix at P. So it does not make sense to say the Jacobian matrix is non-zero, but what does make sense to say is the determinant is non-zero. So if the determinant of that Jacobian matrix is non-zero, then we can find U. You can find open sets U and V, Rn. These are open sets. Let's say P is in U, f of P is in V, and f restricted to U will map U to V homeomorphically. And in fact, you can even do better than homeomorphically. You can do something that's called diffeomorphically. Diffeomorphically just means that the mapping is a smooth mapping, and the inverse mapping that goes the other way is also a smooth mapping. That's what that means. So this is called the inverse function theorem. The inverse function theorem basically says, to put it very simply, it says that if the derivative does not vanish in this sense at a point, then locally you have an inverse function. Because locally, going backwards from V to U, that would be your inverse function, at least in the local sense. So this is like a nice example that produces lots of many examples of local homeomorphisms. You just check if the derivative does not vanish. Okay, so let's remove this. So here's a nice, perhaps, exercise, homework exercise. So show if f from x to y is a local homeomorphism, then f is an open map, i.e., if U is open in X, then f of u is open in Y. Not particularly that hard, but it's nice to practice these definitions. So now we finally get to what was the main goal of today's lecture. All of that was sort of the build-up that we should know, and that is the notion of a covering map, which we will spend a big part of our semester exploring. Definition: a covering map, let's call it pi, from X to Y. So this is going to be better than a local homeomorphism, but let's say what the properties are. So X and Y over here are topological spaces, and pi is going to be a continuous mapping. Let's actually assume all spaces are locally path connected. They do not have to be, but in practice, the way this is used in topology and in other areas of mathematics, that's the condition which is satisfied. So you could be more general, but let's not overcomplicate things. So a covering map between two spaces, X and Y, has the properties so the first property is pi is surjective. That's why we call it a covering map, because otherwise that would be kind of bizarre to call it a covering map when there's points in Y that are uncovered by the map. But it's more than that. It's not just surjective. Second property is for any P in Y. Now here you have to be a little bit careful. The point is being chosen in Y. It's not being chosen in X. So every point in Y, we can find, and we can always assume that this is path connected. We can find a path connected open set. Let me write it like this: a path connected U, this is open in Y, with P in U. There are some books, so depending on what sources you use, depending what book you open up, there are some books that do not assume that this open set is path connected. But if we assume our spaces are locally path connected, you can always take, so you have to go back to the definition of what it means to be locally path connected. It means for every open set containing a point, you can shrink that open set into something even smaller that is path connected. So that's why you can just assume outright that this open set is also path connected. And this is kind of where this assumption that it's locally path connected is helpful. So we can find the path connected open set. So you can find an open set, but you can just assume it's path connected from the very beginning, containing the point, so that if we write pi inverse of u, so this is the pullback. So if you pull back that open set, so at the moment, this is an open set in Y. When you pull it back, you get an open set in X. Now, U is path connected, but when you pull it back, it's not necessarily path connected. So that if we write pi inverse of U in path components, so pi inverse of U, you can write it as a disjoint union. So VI are, of course, open sets in X. And the reason why you know they're open sets in X, by the way, is because that's, again, we're assuming our spaces are locally path connected. The path components, so pi inverse of u, the path components of pi inverse of u, this is an open set, they will be open subsets of u. So they're also open subsets of x because of openness as a transitive property. So again, this is where the local path connectedness is useful, because then that proposition that we mentioned earlier applies. The path components are going to be open. So pi inverse of u, when you write it as a union of its path of these open sets, then pi maps each vi homeomorphically onto u. Now again, we're being a little bit sloppy over here technically. Well, okay, you can say pi, but maybe you can say, maybe more carefully, if you take pi and you restrict it to each of these sets vi, then you have a mapping from vi into u. You know it has to go into u. It has to go into u because pi inverse of u, these are the collection of all points that by definition get mapped to u under pi. So you know they're going into u. And what we're claiming is pi is mapping every one of them homeomorphically onto u. That's what we're saying. So that's what we call a covering map. Now I want to just clarify something that will hopefully make this a little bit easier. So if f is a continuous map and x is path connected, then f of x, so the push forward, and this is of course a subset of y, is also path connected. Intuitively, this should make sense because you have a mapping from x to y. So if x happens to be path connected already, even if y is not path connected, even if y looks something like this, let's say, f is a continuous map. So it's not supposed to tear your space apart into pieces. The space, it's just to stay together. It can twist it, it can deform it, it can take that piece and glue it onto the other piece and can do all sorts of things with it, but it's not going to rip it apart into pieces. So the image of x, f of x, the image of this, however it looks like, it will have to land in one of those. It cannot be in two different pieces because otherwise that's implying you have a discontinuous map. That's the intuition behind that. This is actually very easy to prove. Maybe we make that as a homework problem and then you go ahead and you prove it yourself. However, it's not true the other way around. So the other way around would be, let's suppose you have a continuous map and y is path connected. If you take the pullback, and this is now a subset of x, is not necessarily path connected. I mean, there's lots of very simple examples you can come up with. And in fact, as we look at examples of covering spaces, you will see how that happens. Okay, so that's what a covering map is. And let me just say that, observe, a covering map is a local homeomorphism. But local homeomorphisms, even if they're surjective, because as you can see, one of the requirements of a covering map is it has to be surjective. So you might think, well, maybe if the local homeomorphism was also surjective, then it will satisfy the second property. That's not necessarily true. We'll see examples of that. But a surjective local homeomorphism is not necessarily a covering map? Well, let's explain these. So here's a picture for what a covering map is supposed to be doing. So we're saying that you have X, you have Y, and you pick a point in Y. Okay, so you pick a point in Y, and you can find an open set around that point, U, and then you take that open set and you pull it back. When you pull back that open set, so we can assume that this open set happens to be path connected because of this local path connected assumption. You can assume that this open set is path connected itself. When you take that open set and you pull it back, it's not necessarily path connected, but it will have path components. So you have all, let's say these are your path components that you get. Let's say there's 5 of them. It could be an infinite number, but let's say there's 5 of them. And what do we know about, so this would be pi inverse, that's the pullback. The pullback, by definition, sometimes you call this the inverse image or the pre-image. This will be the collection of all points in X that get mapped to that U, right? They're all being mapped to that U. And they're all being mapped to U. So when we're saying you have a local homeomorphism, you are saying that locally there's a homeomorphism with some open set over here and with some open set over there. So with a local homeomorphism, you're just saying that you can find an open set in X and an open set in Y, so that the mapping, the pi mapping, it will restrict to a homeomorphism locally between those two open sets. But when you have a local homeomorphism, there is no assumption that the other ones, the other open sets that are being mapped to you, are being mapped homeomorphically. Maybe that's the thing. They're not necessarily being mapped homeomorphically into you. Local homeomorphism will just say you can find one of them that's being mapped to you, but not necessarily all of them. And a covering map has this additional requirement that all of them are being mapped homeomorphically to that U. So it's a stronger assumption. So because of this, covering maps are local homeomorphisms, but not necessarily the other way around. So this is the notion of a covering map. Historically, it appeared in complex analysis. That was the first place where it appeared. And then covering maps, they have appearances all across mathematics. You see them in topology, like what we're doing. You see them in complex analysis. You see them specifically when you deal with Riemann surfaces. Riemann surfaces is basically a surface on which you can do complex analysis locally. You see them when you deal with Riemann surfaces. You see them when you work with manifolds, and so on and so forth. So they appear quite a lot throughout mathematics. So this is one of the reasons why we want to treat covering spaces in this course with good detail, so you're comfortable with what they are, so that if you see them again, you have experience with them. So now let's look at some examples. Just maybe I should say some terminology. So when you have something like this, you say, so pi is a covering map. And you would say that X is a covering space over Y. That's what you would say. But here you have to be a little bit careful, because this is a little ambiguous. Technically, a covering space comes with a map, with a covering map. So maybe more appropriately, you would say something like X together with this mapping pi is a covering map, is a covering space. You would not say that a space itself is a covering space. You really have to say a space together with a map is a covering map. It's a covering space. But then you can just maybe just write something like that down and say it's a covering map. So it's just some terminology. So if you're wondering what the difference is between a covering map and a covering space, they mean the same thing. Covering space is just referring to the space which is covering Y, but that would not make sense. You cannot say a space covers Y. A space together with a mapping covers Y. That would make sense. So here's the example. I want to begin. So this is perhaps this is the picture you often want to think of. This is like the go-to image in your head of when you're thinking of a covering map. So in this picture, you let X be any space. I mean, does not even have to be locally path connected, but you just pick any space. No, I'm sorry, Y is any space. Yeah, Y is going to be any space. And X is going to be Y, and then you just take a product with a discrete set. Let's say the numbers 1, 2, 3, up to n. So if you find that confusing, this is like the Cartesian product. So all you're saying is this is going to be the set of points y comma I, where y will range from 1 to n, and y is in y. I mean, that's kind of the way you would think about it. So to use a picture, let's say y is some kind of region in R2. So y is going to be some kind of region in the plane in R2, and x is times 1 times 2 times. So that means it's the same region, but you have an additional coordinate. So you set the additional coordinate to be 1, the additional coordinate 2. So you have the same picture appearing on top of itself n times. So you have this one. So this is at level 1. This is at level 2. This is at level 3. It's the exact same picture, but it's just one level above. This is at level n. So this is y, and this entire thing over here, this is what is now x. This entire thing is now what you're calling x. And then the covering map from x to y is very simple. If you take something in x, it will have its last coordinate will be some integer between 1 and n, and then whatever that is, that's something in y. Let's write it as lowercase y. And then the projection map, or the covering map here, is just y itself. You just drop off that very last coordinate. It's just y. You just drop it off and you send it down to y. This is clearly a surjective map, and it satisfies the required property for very trivial reasons. Because what's the definition of a covering map? So we have to show that for any point in y, you can find an open set, so that when you pull back that open set, you can write it as this disjoint union, and all of those sets get mapped homeomorphically to y. And that's exactly what's going on over here. Because, I mean, maybe I should write it out a little bit more carefully. So to show that pi is a covering map, we pick y in y, and we need to choose an open set u, an open set in y, so that if pi inverse of u, if you take the inverse image and you write it as a disjoint union of open sets in x, then each ei is mapped homeomorphically onto u by the covering map pi. And how do you pick the open set? Well, here the open set can be chosen as large as possible. So you can pick your open set to be y itself. Because this example is so simple, you can just pick this to be y itself. And then pi inverse of y, this would actually be equal to x, right? But x is the union of all of those levels, where from 1 to n of all vi, where vi represents each of these levels, right? This would be v1, v2, and so on. And then you can see that each of these levels, each of these floors, is mapped homeomorphically onto y. So this example is called the stack of pancakes. And this is often the way people visualize a covering map, that when you take an open set and you pull it back, it pulls back to like a stack of pancakes above of it, and each of those, anything in that stack, is then mapped homeomorphically to that open set. Now this example is very, very simple because we can get away by choosing our open set to be as big as possible. most of the time we have to pick something smaller. But in this case, we can get away with it because the covering map was so simple. So this is like a very basic example, but I think it's helpful because it provides you with a picture to think of as we do it. Now, the example that we really want to get to, and this is like the super important example, has to do with the circle. So this is perhaps the simplest important example. It's fairly simple, but it's fairly important in the subject. So the simplest important example of a covering map. So in this example, pi, well, maybe before I write anything down, let me just write some notation. S1, this is the one-dimensional sphere, which we typically call the circle. Unless you're a topologist, then the circle is called a sphere, one-dimensional sphere. And the way we typically write this, the circle is we prefer to use complex notation. So we say it's complex numbers with the property that its absolute value is equal to 1. So in this example, we have the following covering map, pi. So pi is going to map the real line to the circle, and is going to be defined by, so I have to define how this mapping works. This is going to look a little bit funny, but I'm intentionally doing it because it looks funny. So pi over real number. So let's say our real number is denoted by the variable t. So we have to say what it does to a real number t. And we're going to use Euler's formula here. We could write e to the it, because by Euler's formula, that's cosine t sine t, cosine t plus I sine t. And because cosine squared and sine squared adds up to 1, that's going to give you something on the circle. But sometimes people put like a pi over here, a 2 pi I. So I'm going to write it using, I'm going to speed up the curve by a factor of 2 pi, so 2 pi it. And the reason why this looks funny is because we have two different pi's. This is the projection, this is the covering projection map, this is the number pi, and then later on, when we talk about the fundamental group, we'll have pi 1 as in the fundamental group. So that's how you know you're doing some hardcore mathematics, when pi means so many different things all at once. But I'm sure we are mathematically mature enough to distinguish between those two pi, so we'll leave it like that. So this mapping is a covering map. Let's draw a picture. So this is our unit circle S1. This is the real line R. So to be a covering map, we have to go through the properties. The first property is pi a continuous mapping? It is, because it's given by an exponential function. That's a continuous function. That's just standard calculus stuff. That's a continuous function. So pi is a continuous mapping. Is it surjective? Is it true that every point on the circle has this form? Yes. Because if you give a point on the circle, okay, so if you give me a point on the circle, let's say this is your point P, then a point on the circle can be written as e to the I theta, where theta is this angle that it forms. And then, so then P can be written as e to the I theta, and then so you set, so then pi applied to theta over 2 pi will give you back P, right? Because how is this defined? This is e to the 2 pi I applied to whatever that is, theta over 2 pi. You cancel the 2 pi's, that's I theta, so that's P. So the point is, every point on the circle, it comes somewhere from the line. Basically, you just take the angle, you divide it by 2 pi, and you found a point on the real line that gets mapped to that point. Well, actually, you have lots of points that do that for you. That's just one point, right? So you found one of them, right? So if you found a point, so if you found the point P, So you can find a point P. So given a point, you can find something on the real line that maps to that point. But because this is a periodic function, if you add 2 pi to it, so let me just show you what happens if you add 2 pi. So let's say let's say e to the 2 pi I t is equal to p. So you found something, let's say t, on the real line, and t is being mapped to this point p. So we're showing that this is a surjective mapping. So it's being mapped to p. Then look what happens if you add e to the 2 pi I t and you multiply it again by 2 pi I. That will give you p again. The reason for this is because by Euler's identity, this is cosine 2 pi plus I sine 2 pi. So that's 1 and that's 0. That's just 1. That's just a complicated way of writing the number 1. But this, of course, if you add the complex exponentials, this is 2 pi I t plus 2 pi I. And if you factor out the 2 pi I, this is 2 pi I t plus 1. So if you found the t that goes to p, then you can translate everything over by 1. So t plus 1 is also being mapped to p. You can also translate back t minus 1. You can translate again t plus 2. You can go back t minus 1. And you basically have equally spaced points, and all of them are being mapped. So all of these points are being mapped to this one single point p. So it is a it is a surjective mapping. It's a surjective mapping. So the next question is, how do we know? So this is the next question. So we need to show. So to show that pi from the real line to the circle S1 is a covering map for each P in S1, we need to find, and as we said, you can just assume it's path connected. We need to find a path connected open set U, so an open set on the circle, so that if you pull back that open set, you pull it back to the real line. And when you pull it back to the real line, it's not necessarily going to be connected, but it will have path components. So you can write it as a union of path components. And each VI is mapped homeomorphically onto U by this covering map pi. That's what we need to show. So that's the definition of a covering map. And instead of writing out like a formal proof of this, which is not very illuminating, I think it's more helpful to just see the idea of what's going on. It's basically the picture that we drew over here, that if you have a single point and you pull it back, when you pull back this point P, there is some real number that maps to that point, but the other points that map to it are all translates. Integer translate. You're just translating the integers. They're integer translates that are all being mapped to p. So now, if you draw, I guess I should have mentioned this earlier. I keep on forgetting to say it. So we need to find a path connected open set with this property. So this such an open set is called evenly covered. So that's the terminology. It's an evenly covered open set. The idea, of course, is that when you pull it back, every one of the pull-backed open sets is being mapped homeomorphically. So they're all sort of the same thing. That's why we call it evenly covered. It's sort of the same throughout. Evenly covered open set. So instead of writing this entire sentence over and over again, you can just say, we need to find an evenly covered open set. And we can always assume it's path connected itself. I just keep on saying that because depending on the book that you use, some of them assume that things are path connected, some of them do not. But I just thought it would be more convenient to just assume from the very beginning that all of our spaces are path connected I'm sorry, are locally path connected, which means we can just assume that our open sets that we choose are path connected themselves, because we can always shrink them to be small enough to be path connected. So I think that makes things a lot simpler when we're doing that. So then the idea would be that if you were to draw a little neighborhood around that P, little neighborhood around that P, then you would draw a little neighborhood around every single one of these. And if the neighborhood is small enough, then none of these red intervals are overlapping. And then look at this. Each of these ones are being mapped homeomorphically by pi. Pi is a bijection on each of them. They're all being mapped homeomorphically in a bijective way around that little interval, that little arc, open arc around the P. Now, of course, if you choose, so look at this, if you choose the arc to be everything, if you choose this to be everything, right, if you make this be too big, so if you make this go all the way around, then you will completely fill this up. And then it's no longer true that pi is mapping this entire interval homeomorphically to that anymore, because the line is not homeomorphic to a circle. So that's why it has to be sufficiently small enough. But this is like the go-to example, probably the most, well, the go-to example for intuition is the stack of pancakes that we drew. But this is kind of similar. It's just not as, you can say, the picture might not be as nice, because this is sort of like an infinite stack of pancakes that are being mapped homeomorphically to that. Now, here is another example. This is somewhat similar. So this is another example, also with the unit circle. So in this example, pi is a map from the unit circle to itself. So we have to say what it does to a point on the circle, and we represent the point on the circle with a complex number. And what this map does is it takes that complex number and it raises it to the power n. So if something has absolute value 1, then raising it to the power n will still have absolute value 1. So it is a mapping from the circle to the circle. It's continuous because this is just z to the n. That's continuous. And in a moment, we will see why it is surjective. So we claim, so this map is also a covering map. So let's check why that's the case. So here n is an integer. It cannot be 0. If it's 0, then this is just a constant. A constant mapping is not surjective. So it's a non-zero integer. It could be negative, but let's just assume it's a positive. Let's just assume it's a positive integer. That this is a covering map. So here's the way the picture goes. So we have our circle and we have a circle. And so this is S1, this is S1. Let's say we pick a point P on the circle. Then just like before, we can write P as e to the I theta. Right? There's this angle that's being formed theta. So we can write it as e to the I theta. Now we want to find something on this side. We want to find a point over here. Let's call it Q. That is being mapped over to that point. So because that point is on the circle, it has its own angle. And let's call that angle phi. So Q can be written as e to the I phi. And we want pi of Q is equal to P. So we're trying to argue that this mapping, it's surjective. So you're trying to find the point that gets mapped to it. Now, let's work this out. So this is, so pi of Q, that's pi of e to the I theta. So that's e to the I theta raised to the n. Now you have to be a little bit careful here. If you raise a complex number to a real number, it is not necessarily true that you can multiply the exponent in. So let me just show you what I mean. E to the pi I, e to the 2 pi I is equal to 1. So then you can say, oh, I can take to the, let's say, to the pi over here and to the pi over here, and then you end up with e to the 2 pi squared I is equal to 1. But then the problem is you get cosine of 2 pi squared plus I sine 2 pi squared is equal to 1 plus 0I. And then you have shown that cosine of this is equal to 1, which is not true. That's not true. This is like a good puzzle you can ask people to figure out what the mistake is. It looks correct, but the mistake is you're not allowed to multiply. So the rule, the multiplication rule for multiplying an exponent into a complex number, it does not work. There is no such rule. It breaks apart. It only works when you have an integer. If you have an integer, if this number is, let's say, like 4, then you can do it. Because if it's 4, then you're just repeating this 4 times. And when you repeat it 4 times, you are allowed to add. And by adding, you're adding 2 pi I 4 times. So you can only do it when you have an integer. So that's just a very small, subtle point in case you do not know that. But because this is an integer, you can put that in there. So this is e to I theta n. And that's supposed to be equal to p. That's supposed to be equal to e to the I. I messed something up. This is not supposed to be theta. These are supposed to be phi. So this is I phi, I phi, I phi n, and this is I theta. And now you equate the exponent. So if this is equal to this, then it means I theta n is equal to I theta up to an integer multiple, 2 pi k for some k in z. And now if you, small mistake, I keep on writing theta. I meant to say phi. And this is supposed to be 2 pi I 2 pi k. So now if you do some cancellation, cancel the I and cancel the n, we get that phi. So the way you find the angle, you take theta, you divide it by n, and then you add to it 2 pi of the multiple of the angle. So if you set k is equal to 0, so these are the choices for phi that you get. So phi would be theta over n plus 0. Phi would be theta over n plus 1 plus 2 pi over n. Phi would be theta over n plus 2 pi over n times 2. This is k is equal to 2. You would have theta is equal to theta over n, phi is equal to theta over n plus 2 pi over n times 3, and so on. And this will go up until you have theta over n plus 2 pi over n times n. But when you reach n, you're getting phi is equal to theta over n plus 2 pi. But as far as the angle in the picture is concerned, that's the exact same. That's the exact same point. So that's going to be the exact same point. So basically, the way this works. So to basically summarize this, let's say the mapping here f of z was the mapping z cubed. To show you an example, and let's say that this is a 60-degree angle. The way you get all of the points in the circle that get mapped to that is you cut the angle by n. You do theta over n. You cut the angle by n. So in this case, you're cutting it by 3. So if you cut the angle by 3, you get 20. So you're getting an angle over here, 20 degrees. So that angle is being mapped to this one. But then to get the other, that's not the only point that goes to p. There's other points that get mapped to p. To get the other points that map to p, you have to do this. You have to do 360 degrees divided by 3 in this case. So that would be 120. So then you keep on adding 120. So you add 120, and so 360 divided by 3, 120. So then you keep on adding 120. So you would have 140 somewhere over here. And then you add 120 again. So that would be like 260. I guess like over here, 260. And if you add 120 again, then you return back to where you are. So that's basically the way that it works. So the inverse image of this point is going to be 3 points that are all like equally spaced apart. And in general, if this is n, you will have n equally spaced apart points. So now look at this. Let's say, yeah, so we're going to have 3 points, and they have to be, in this case, they're going to be equally spaced apart. So they will form the vertices of an equilateral triangle. And it will be a regular n-gon. So now, if you draw a little, you want to find an evenly covered neighborhood, evenly covered open set. So to show that this is a covering map, you have to find a small enough open set. So if you draw this sufficiently small enough, like this, then what's going to happen in the picture is that this piece, it gets something like this, and then something like this, right? So that's what you're going to have. So if it's sufficiently small enough, then when you draw these 3 open arcs, they're not going to be crashing into each other. So you have 3 pieces, and all of these 3 are being mapped homeomorphically to this arc by using this mapping z cubed. So that's sort of like a picture to convince you why these are also covering maps. Now let me give you an example of something that's a local homeomorphism but is not a covering map. I think this is helpful. So this is an example of a local homeomorphism, and this will even be a surjective local homeomorphism, but is not a covering map. So here we're going to have the following function. It's going to go from the positive real line to the circle, and this is going to be f of t is e to the 2 pi I t. So it's just like before, except we're not using the entire real number line. We're only using the positive portion of the real number line. And let's see what the problem is. Now, this is clearly surjective because every point on the circle can be represented as a positive angle by, right, so it can be represented like this. But what exactly is why is this not a covering map? So this is the positive real line. This is 0, this is infinity, so this is r plus. And you're mapping this to the unit circle. And the problem will occur at 0. So 0, f of 0, is supposed to go to e to the 0. It's supposed to go to 1. So this is 1. This is 1 plus 0i. That's where the problem will occur. Now, let's convince ourselves. Well, it's showing why it's a local homeomorphism is not going to be difficult, because basically, let's find the inverse image of 1. It cannot be 0, but it would be 1, 2. Maybe I should not do it like that. Let me use the same color. So it would be 1, 2, 3, 4, and so on. And now if you draw a small enough, if you have a small enough arc, open arc, then when you pull back that small open arc, you have these pieces. Okay, and all of these pieces are being mapped homeomorphically onto that piece. So when you look at that, you're like, well, why is it not a covering map? Well, because you also pick up something else. You see, you're also going to pick up, you see, this is 0 and that's positive. So you're really going to be picking up this. But you have to understand 0 is not included. So you're not going to have the other part of, the blue interval. And the issue is that this function f, it is mapping each of these blue pieces homeomorphically to that blue piece. So for that reason, this is a local homeomorphism. Each of these is being mapped homeomorphically to that one. So it's a local homeomorphism. But what about this one? You see, the definition of a covering map is then when you have an evenly covered neighborhood and you pull it back, each of the components, not some of them, because you have some of them, the ones at 1, 2, 3, 4, and so forth, each of those is being mapped homeomorphically to that blue arc. But you have to show that every single one of the path components is mapped homeomorphically to that blue arc. But this one is not. This one is not. This mapping over here, this is not surjective. Because the part, like for example, that red point, you see the red point? That's not part of that piece. So it's not mapped, that piece is not therefore mapped. It is mapped injectively there, that's true, but it's not being mapped bijectively. There's no bijection between that and that. So because of this, this is not a covering map. So it's very close to being a covering map, very, very close, but it's not a covering map. There is an issue that occurs. But it is a local homeomorphism, because local homeomorphism, to put it very simply, says that you can find an open set in one space and an open set in the other space where F provides a homeomorphism. And every one of these is mapped homeomorphism. You can find an open set here and an open set there where F provides a homeomorphism. But to be a covering map, the requirement is more than that. When you take that open set over in Y and you pull it back, when you pull back that open set, all of the pieces, all of those component pieces have to be mapped homeomorph, not some of them, but all of them. And there's a problem that occurs over there. So that's a nice example to have in mind. And maybe I'll finish with this. This is similar. So this is very similar. This example is very similar to the example that we have from R to S1. And here the map will rather go from the complex plane to the punctured plane. So this is the punctured plane. And the mapping here is pi of z is equal to e to the 2 pi I z. And I'm going to draw a picture. So this is C. And this is the punctured plane. So it's missing the origin. And in this example, if you pick the point P, when you pull back P, it's basically like a logarithm or something. But yeah, so maybe that would make like a good exercise problem for you to think about this, to draw some pictures. But basically, you're going to get something that goes like this. You're going to have lots of them. And if you have like a piece over here, you're going to have like different, they will not necessarily all look the same. They could have smaller and bigger sizes, but this is sort of going to be the picture that you get. It's actually very similar to the previous one. In this example, you were confining yourself to a real variable, but you can actually do the same thing when you allow this to be a complex variable. So this is like another example of that. So we'll finish here on covering maps, and next lecture we'll discuss some very basic properties that covering maps have.